Hey guys, welcome. Yeah, so if you haven't already done so, then watch examples 0 and 1. In example 0, the most important example, we saw how the delta-epsilon limit definition is essentially the same in Calc 2 and in multivariable calculus or Calc 3. I say it's essentially the same because, well, the delta-epsilon limit definition for a function of two variables, f of x comma y, as we saw in example 0, is analogous to the definition for a function of a single variable, f of x. Now, I needn't say more because, well, we explained thoroughly in example 0 how they're analogous, and so watch example 0. It's got a nice visual and a thorough explanation of how multivariable limits work and why they make sense. So check that out. But in example 1, we had three problems, right? Three limit evaluation problems where all three limits did not exist. And so then hopefully the limit here is going to exist. And spoiler alert, it does, right? Like, so this will be our very first delta-epsilon limit proof in Calc 3 or multivariable calculus, because as I said in example 1, all three limits that we evaluated ended up not existing, and the way that we checked that the limits didn't exist is by approaching them from multiple different lines and seeing that eventually they didn't come out to the same number. So here what we would have done initially is what we would have done in example 1, which is approach 0, 0 from a few different lines, but we do that here and we keep getting the same value. We keep getting the same limit value, that is 0. And so we go, alright, so the limit must be equal to 0. That is, this here must be equal to 0. But then, you know, even if you checked it from 10 different lines, that's not sufficient. You need to check it from infinitely many directions, but that's not possible. So then the way that you show that this limit is in fact equal to 0 is by doing a delta-epsilon limit proof. And so our first one here, in examples 3 through 5, you will have to similarly write delta-epsilon limit proofs because, well, they all exist. And recall that the delta-epsilon limit definition that we saw in example 0 goes a little something like this, which is for every epsilon greater than 0, an arbitrarily small positive number, that's epsilon, we need to find, not even want to, but we need to find a delta greater than 0 such that whenever this is true, then this follows. And if you want me to kind of spell it out in the way that we did in example 0, well, for every epsilon greater than 0, we want to find a corresponding delta greater than 0 such that if 0 is less than the square root of x minus a squared plus y minus b squared is less than delta, then the absolute value of f of x minus L is less than epsilon. That was the formal definition that we gave in example 0. Well, clearly the limit point a comma b here is 0, 0, and that's why the x minus a squared here is just x squared, because a is 0, and the y minus b squared here is just y squared. And f of x minus L is the limit value. For anything else, watch example 0. I'm not going to explain this any more than I just did. And if we write this a bit more succinctly, this here, because, like, you know, we can clean up in this part, for example, then we can write the following, which is that this turns out to say that whenever this is true, we need the following to follow. Okay, so look here. This here is just this here. So again, as I claimed, this here, what you see here, is a mere succinct rewriting of this. It's an abbreviated writing of this. Well, in this part, I'll justify why this here and this here are the same. Well, if you use absolute value rules here, once you get rid of the minus 0, obviously the minus 0 we don't need, and so you'd have absolute values around this quotient. And so then absolute value rules would say that you could give the absolute value to the denominator, but these guys are always positive, right? So you don't need the absolute value. So therefore there, and then the absolute value around this whole thing in the numerator can be absolute value around individuals here that are in the product. and 3 is already positive, so it doesn't need the absolute value. X squared the same, and so then you keep the absolute value around only y. Yeah, okay. So basically, this here is just the definition we stated here, right? Like, we're still in the definition. Okay. So, like, the way you'd move forward is at this stage, once you get to something like this, you'd manipulate this quantity in the manner that I'm going to show you. Now, this is really your first example on writing a delta-epsilon limit proof in multivariable calculus. And so, there are varieties, and the varieties you'll be exposed to in examples 3 and then 4, and then a very interesting, unique one in 5, a bonus example. So, by that time, you will have had all the tricks of the trade, so to speak. Okay, now, this is the kind of observation you need to be able to make once you get to a place like this, right? Like, now, as I said, we're going to manipulate this, and also, as I said in example 0, at some point in our delta epsilon limit proof, we need to use this restriction on delta. You'll see where we're going to use it here in this proof. But anyway, we make this observation, and this observation is crucial because, well, first of all, let's explain why this has got to be true very briefly. Obviously, if y squared is 0, which is the worst it could be, right? Y squared is at smallest 0, and if it's equal to 0, then the equality part of this lesser or equal to is maintained. X squared will equal x squared. But if y squared is anything but 0, then clearly the left side is smaller than the right side here. And so this inequality is true. Now, from this inequality, we can see that x squared divided by x squared plus y squared is going to be less or equal to 1. Given this, x squared divided by x squared plus y squared has to be less or equal to 1. And so that's why we liked this observation, because now we can use it to write this, which is embedded in this expression that we want to manipulate, right? Now, look. If this here is less or equal to 1, and it's obviously less or equal to 1 because, well, this is true, meaning the denominator is either equal to the numerator or bigger than the numerator. So when the denominator is equal to the numerator, then the equality part here, so we get 1, right? But when the denominator is bigger than the numerator, we get something less than 1, but positive, because everything in this quotient is positive, and therefore we get this inequality. Now, if this is true, then notice that this whole quotient has to be less or equal to 3y, because, well, 3 times the absolute value of y, I should say. Because if you had 3 times the absolute value of y and you multiply by this, then this is going to make it either equal to 3 times the absolute value of y or smaller, because this is less or equal to 1, so it will shrink 3 times the absolute value of y or leave it alone, right? Okay. So, I'm saying this here, right, is less or equal to 3 times the absolute value of y. Now, there are a couple of nice definitions of the absolute value, and one of them said that the absolute value of y, say, is equal to the square root of y squared. Now, that definition makes perfect sense and is explained in my high school algebra video, so I'm not going to take the time to explain it, but the square root of y squared is clearly the same as the absolute value of y. So then what I've done in going from here to here is mere rewriting of the absolute value of y in this manner. But now look at this. Well, observing this, right, since x squared is less or equal to x squared plus y squared, we can write something similar for y squared, which is y squared is less or equal to y squared plus x squared. And then we can have that inside the square root, what I just said, and therefore move in this direction. And now, notice that this here is exactly this here. And so it is here where we're going to exploit this restriction on delta. Yeah? Okay, so again, this makes sense going from here to here. That's just definition of absolute value. And then from here to here, I use this fact, right? The fact that this is less or equal to this here, and therefore the square root, which is an always increasing function, is going to retain the inequality, right? And obviously they both have 3, and then this here is going to allow us to involve a delta, and so that's why this was a move in the right direction, and it was nice. Okay, less than 3 delta. Now look at what we accomplished. We just said that whenever this is true, then this here is lesser or equal to 3 delta. And remember, the whole point of writing a delta epsilon limit proof is to eventually come up with a generic relationship between epsilon and delta that always prescribes what delta should be for any epsilon. So here we are, because if we have that whenever this is true, right, whenever this restriction on delta is true, that this here will be less or equal to 3 delta, then what we should do is choose epsilon to be 3 delta, right? Because what I'm saying is we should do this. And then from here, remember, what we want to do is define delta in terms of epsilon. And so, like, that amounts to dividing this equation by 3 on both sides. And so then we get delta is equal to epsilon over 3, right? Okay, cool. Alright, so in examples 3 through 5, I'm not going to do what I'm going to do in the following minute, which is check that we have found the correct delta. This checking part is not necessary in your delta epsilon limit proof writing, but here I'll do it with you. We'll just check together that we have in fact come up with the correct relationship between delta and epsilon. Okay, so we're saying if this is true, right, then we want this to be less than epsilon. Well, notice that whenever this is true, by everything that we had written over here that I erased, we know that this here is first lesser or equal to 3 times this here. We'd gotten there, right? Okay, cool. Fine. But then this is saying that we have, well, let me color code it to make it more familiar, like as I had done in the past. I didn't change anything. I merely just, and also swapped the place of, yeah, addition is commutative. You know it. Okay, so we're here, right? And then now I could say that this here is strictly less than 3 delta, right? But then we said that delta is equal to epsilon over 3, so I'm saying that this here is strictly less than 3 times epsilon over 3, and therefore we just saw in our check that whenever this is true, this will be less than epsilon as desired. Yeah, okay, cool. Alright, so this is a good first example in writing delta epsilon limit proofs in multivariable calculus, but you need additional practice, and that's examples 3 through 5, so look out for those videos. I hope you enjoyed this and learned a lot. Keep watching. Take care.